All right, well, welcome everyone to this Monday feature of Magnetosphere online seminar series. We're pleased to have Lauren Blum with us here, and Lauren, feel free to stop sharing the screen so you can start sharing your slides as well. I'll give you an introduction here. Okay, great. So Lauren Blum is an assistant professor in the Department of Astrophysical and Planetary Sciences at the University of Colorado Boulder. And prior to 2020, she was a research scientist at NASA's Goddard Space Flight Center. Her research interests include heliospheric physics and the coupled nature of plasma populations in planetary magnetospheres. In particular, recent work has focused on wave-particle interactions, solar-wind magnetosphere interactions, and energetic particle dynamics in Earth's radiation belts. Her experience includes analysis of particle and field measurements from satellites, balloons, ground stations, as well as instruments in small satellite development. So with that, Dr. Blum, feel free to take it away.
Great, thanks. And just to check, you can see my slides and hear me okay?
Yes, everything looks great.
Okay, thanks so much. Well, thanks for having me, and thanks for everyone for joining. So today I'm going to talk about energetic electron precipitation. And I know that the past few talks, we've heard a lot about different wave populations in the inner magnetosphere. And we had a nice talk on particle precipitation last summer, actually, from Wei Chao too. And so what I thought I'd focus on here to kind of distinguish it from previous talks is really looking at the properties of energetic particle precipitation, in particular from an observational perspective. And so I'll talk a little bit about the physical drivers of precipitation, what wave modes or processes can scatter particles into Earth's atmosphere, and then also about the impacts of energetic electron precipitation, both the implications for radiation belt dynamics, as well as changes in atmospheric chemistry. And I did just want to note that some of this content is written up in a chapter that Aaron Brenneman and I wrote a year or two ago now that is in a book that was edited by Allison Janes and Maria Usanova, focusing on loss of energetic particles from the radiation belts. Okay, so I wanted to start with our motivation and why we're interested in studying energetic particle precipitation, and in particular, kind of high energy electron precipitation into Earth's atmosphere. And so one of the main motivations is the relationship of precipitation to radiation belt dynamics. And this is just a slide I like to show, showing some of the early measurements from the Van Allen probe's REPT instrument, looking at 4.5 MeV electrons in L shell and time, where color is the flux or intensity of particles. And what you can see is that the outer radiation belt is highly dynamic and can vary on timescales ranging from minutes or hours to decades or with the solar cycle. And that a number of geomagnetic storms occurred during this period, some causing these very rapid depletions in high energy particles, and others causing rapid enhancements or acceleration. And I think throughout the Van Allen probe's era, there's been a lot of progress made on understanding these acceleration or enhancement events and what types of processes can accelerate particles to multi-MeV energies on these types of timescales. But there's a lot more questions remaining about the depletion or loss of these high energy particles, both during the very rapid dropout periods or depletions during main phase of geomagnetic storms, as well as the kind of more gradual decay of the outer belt. And so the big question is whether electrons are lost out through the outer boundary of the magnetosphere, the magnetopause, or into Earth's atmosphere via precipitation. And that's what we'll look at here a bit. And so there have been a lot of modeling and data analysis efforts to try to understand these dropouts or depletions in the outer radiation belt. And often there's significant loss to the outer boundary through magnetopause shadowing. But very often additional loss processes are needed in models to fully capture these rapid depletions throughout the entire radiation belt. Particularly at lower L shells, so the inner edge of the outer belt, as well as at higher energies. And this is just one example from a paper by Tu et al., where the observations from the Van Allen probes are shown on the top and model results on the bottom. And you can see that at the lower energies, the model reproduces this enhancement during the geomagnetic storm very, very well. But at these higher energies, the kind of red and orange lines here, there's a depletion observed that isn't as well captured in the model. And so there have been a number of studies showing that additional loss is needed, likely to Earth's atmosphere, but being able to understand when and where and why, what's causing it, is kind of the next step. So the second motivation is actually the impact of these energetic particles once they've been lost from the radiation belt on Earth's atmosphere. And so high energy electrons and protons can ionize the neutral atmosphere and cause enhancements in odd hydrogen and odd nitrogen, so HOX and NOx in the mesosphere region. And this can subsequently cause depletions in atmospheric ozone. And so some of the critical things to characterize in relating to precipitation are the energies of the precipitating particles and the fluxes, as well as the kind of spatial areas that they're occurring over, to better understand the impact of these particles on the atmosphere. And there was a nice study by Seppala et al. Modeling the impact of microburst precipitation, so one type of high energy electron precipitation, on atmospheric chemistry. And so here we're looking at percent changes in HOX, NOx, and ozone for both the summer and winter hemispheres. So you'll note that it makes a difference, not just how much precipitation is occurring, but where and when. And then they've also run this for both mean electron fluxes as well as median fluxes found in microbursts, and you can see a large difference there as well, suggesting that it's really important to really well characterize precipitating fluxes and energies to better understand how this flows through to atmospheric chemistry changes. Okay, and finally, just the third motivation, at least for me, is that particle precipitation is really a universal process. And so this is the same type of process that generates the aurora at Earth of particles precipitating into Earth's atmosphere. In general, the aurora is generated by lower energy particles, but we're kind of studying the high energy tail of this population, so the MeV, or hundreds of keV electrons, which, rather than producing visible light, can result in production of X-rays instead. And that these auroral processes don't just happen on Earth, but they happen at lots of other planets within our solar system, both magnetized and even ones without large-scale dipolar fields, such as Mars. There have been some recent measurements looking at both diffuse and discrete aurora on Mars by the MAVEN spacecraft, as well as the recently launched Emirates Mars mission, EMM. Okay, so now that we know why we're interested in energetic particle precipitation and why we want to study it, I thought I'd highlight some of the outstanding questions, or what we want to know about the precipitating populations themselves, to better understand how they contribute to radiation belt dynamics, as well as changes in atmospheric chemistry. And so we really need to know when, where, and how much precipitation is occurring within the magnetosphere. And in particular, some of the questions that will help us answer this are better understanding the global distributions and spatiotemporal characteristics of precipitation regions. What's the actual energy range or energy spectrum of precipitating particles? And then finally, what mechanisms or wave modes are actually responsible for the precipitation? And so throughout this talk, I thought I'd focus mostly on kind of the open questions and what we need to know, rather than what we know already. But I'll start with a little bit of background just on energetic particle precipitation in general, and in particular, how we actually measure it or observe it at Earth. And then briefly touch on some of our current understanding of what's driving different precipitation types. But then from there, I really wanted to highlight some recent advances and remaining open questions related to particle precipitation, including where, when, and how much is occurring. And then I'll just end with a little bit of a look forward on some upcoming efforts to better understand energetic particle precipitation. And I know the past few talks went into kind of the basic physics in a lot more detail, so I didn't want to repeat that, but I thought I'd just highlight very quickly that we're really interested in this bounce motion, or kind of the second adiabatic motion of energetic particles in the magnetosphere when we're looking at precipitation. And a particle will precipitate into the atmosphere when its pitch angle or angle relative to the background magnetic field is small enough that it actually impacts or can interact with the atmosphere before mirroring and returning to be trapped in the magnetosphere. So we're interested in low pitch angle particles that can actually reach the atmosphere. How do we actually measure particle precipitation? And so there's a number of ways to directly measure it. We often use low altitude satellites. And this is because at higher altitudes, the loss cone or the pitch angle of particles that will actually be lost to the atmosphere is relatively small. And so it's difficult to resolve. But at low altitude, this loss cone opens up and you can directly measure these precipitating particles and separate them from the trapped population. But there are actually a number of indirect measures of precipitation as well. And so I won't go into detail about these, but they each have kind of their benefits and caveats, I'd say. And so low altitude satellites are moving very quickly at about 7 kilometers per second along their orbit. And so they're cutting through precipitation regions very rapidly. But balloons, on the other hand, can actually kind of sit in a stationary location and better measure the temporal changes of precipitation. However, they're not directly measuring the energetic electrons, but measuring instead the Bremsstrahlung X-rays that have been produced as the electrons impact the atmosphere. Rheometers, VLF receivers, and incoherent scatter radar are other techniques to kind of indirectly probe the effects of precipitation and back out what the precipitating population might have been. Rheometers are looking at cosmic noise absorption kind of directly overhead the rheometer. And so they often respond to energetic particle precipitation above about 30 keV. VLF receivers, on the other hand, are measuring the signal generated by VLF transmitters, so kind of Navy transmitters or other artificial transmitters on Earth. And so they're measuring the change in the ionosphere along the path between the VLF transmitter and the actual receiver. And so you're getting a somewhat integrated effect of particle precipitation on the ionosphere. And then lastly, incoherent scatter radar can probe the density of the ionosphere and look at changes caused by energetic particle precipitation. Okay, and so I'll focus more on the LEO or the low altitude satellite observations. And like I said, they can directly measure precipitating particles, but there are some complications to their observations. And so in particular, for example, if you have a wide field of view instrument at low altitude that's, say it's looking primarily perpendicular to the magnetic field, so measuring locally trapped particles or locally mirroring particles, depending on the altitude and location of the satellite, you could be measuring a number of different particle populations. So untrapped particles or particles in the bounce loss cone that will be lost to the atmosphere within one bounce period will be measured conjugate to the South Atlantic anomaly, whereas quasi-trapped particles or those in the drift loss cone that will be lost within one drift period are measured kind of primarily throughout the rest of the region. And then finally, these low altitude instruments can also measure the trapped population in some regions. And so this is both a benefit and a complication to looking at low altitude particle measurements, that you can both probe the bounce loss cone or precipitating and the trapped particles, but you also have to be careful separating them out from each other based on satellite location and instrument fields of view. So just an example of some measurements from the SAMPEC satellite that was at low altitude and has a very wide field of view instrument measuring greater than 1 MeV electrons, the HILT instrument. So what you often see as it cuts through the outer radiation belt or the foot points of the belt at high latitudes is this kind of slowly varying profile of trapped or drift loss cone particles. And then on top of that, superposed on top, you often get these kind of more rapid enhancements or bursts of precipitation, both on sub-second timescales that have been termed microbursts, as well as these slightly longer duration enhancements that have been termed precipitation bands by some, that last, a few to tens of seconds, but are often seen on consecutive orbits or in conjugate hemispheres. So this duration observed by SAMPEX is likely due to the spatial extent of the precipitation, not necessarily the temporal. So I wanted to also show some measurements from the POSE satellite. So in this case, the instrument's a little different. It's still at low altitude, but they have two telescopes, one nominally pointing roughly along the background magnetic field, or the 0-degree telescope, and the other pointing perpendicular, so the 90-degree telescope. And the POSE satellites are often used to study precipitation as well, in addition to SAMPEX. And the measurements from them look a little different. Here, the black shows the observations from the 90-degree telescope, so primarily trapped population, while the red and blue show the 0-degree telescope, so primarily precipitating particles. And what you can see is, for example, when the 0-degree telescope flux is enhanced, marked here in the dashed line in blue, you're getting an isotropization of the flux. And so particles are precipitating as the 0-degree count rates approach the 90-degree count rates. And so that's just another type of observation that are used extensively to study precipitation. And here there's a number of different energy channels and both ion and electron measurements. So one kind of detail about POSE or caveat is that the 0-degree and 90-degree telescopes are often used kind of roughly to look at precipitating versus trapped populations. But the fields of view of these instruments are rather small compared to SAMPEX. And so the 0-degree telescope actually only measures a small fraction of the full loss cone. And that's what's shown here on the top, this fraction of that bounce loss cone measured by the 0-degree telescope. And then on the bottom here is looking at the 90-degree telescope and the actual fraction of that, those measurements that are observing trapped electrons. And so you can see you have to be a little bit careful, assuming we're measuring all loss in the 0-degree telescope and all trapped particles in the 90, because you are missing a large fraction of the loss cone with these narrower field of view instruments. Okay, so I thought I'd show some more SAMPEX observations of these two different kind of types of precipitation that are often observed, the rapid sub-second microburst precipitation on the left and the longer duration precipitation bands on the right. And these are the global distributions. So we're looking in MLT and L shell here, where color is the amplitude of the precipitation above this kind of background profile. And what you can see is that the microbursts and the precipitation bands have very distinctly different distributions in MLT and L shell. and that these kind of indicate that different wave modes or different scattering mechanisms are producing the two different types of precipitation, with chorus waves over on the morning side often being compared to microburst distributions, and EMIC waves, which can occur on the dusk or afternoon side, being compared to precipitation bands. So this connection between chorus waves and microbursts has long been established, both because of their similar global distributions, so across the morning side and outside of the plasmasphere, as well as their finer scale structure, so the kind of sub-second structure of rising tone elements in lower band chorus, and the sub-second structure of microburst precipitation. In addition to these kind of similarities in temporal and spatial characteristics, there have been some more detailed studies looking at magnetically conjugate measurements of microburst precipitation at low altitude and chorus waves measured near the equatorial plane. And so on the left, we have one example of microbursts measured by Firebird in the kind of few hundred keV energies, and chorus waves measured by the Van Allen probes near the equator. And on the right-hand side, we have now reversed in order, but we have the precipitating electron flux on the top panel and chorus wave amplitude on the bottom. And you can see that there's a lot of similar structure and fine structure, although it's often difficult to get exact one-to-one correspondence because of the very small scale of both of these processes. So this association between chorus waves and energetic electron microburst precipitation has been made both based on simulations and theory, as well as their similar global distributions and these kind of handful of individually magnetically conjugate events that we have. But there's still a number of open questions related to how chorus waves scatter, particularly the high energy MEV range of microbursts that are observed, where the interaction is occurring, whether it's occurring close to the equator or at higher latitudes, as well as what the overall contribution of microbursts is to radiation belt dynamics or loss. So on the other hand, I was showing precipitation bands. And so one mechanism that's associated with precipitation bands are EMIC waves. And we heard a lot about these from Maria Usanova last week, but these are lower frequencies occurring below and approaching the ion cyclotron frequency now as compared to the electron cyclotron frequencies for the Whistler mode waves. And they've been hypothesized to be able to produce MEV electron precipitation signatures across kind of the dusk and afternoon sector. So there have been a number of, again, kind of magnetically conjugate observations linking precipitation bands, relativistic electron precipitation measured by balloons, to magnetically conjugate EMIC waves at the close to the equator, in this case measured by the GOES spacecraft. There have also been comparisons of measured precipitation, in this case by one of the barrel balloons, and compared to kind of modeled precipitation that would be driven by observed waves, and you get very similar profiles and fluxes and energies. And then finally, there have been some more recently observations of actual depletions in these low pitch angle populations of MEV electrons in the trapped population, so measured by Van Allen probes, coincident with EMIC wave activity. And so together, these studies all kind of, the growing number of studies confirm that some of this energetic electron precipitation events are driven by EMIC waves. But there's still a number of questions again here relating to when, where, and how much of this precipitation and those dusk side precipitation events are driven by EMIC waves. So some of it is, but how much? And so lastly, I did want to highlight this other potential scattering mechanism, There's a few other kind of candidates. One is field line curvature scattering that would occur kind of across the night side of the magnetosphere as well, that could scatter MEV electrons into Earth's atmosphere, as well as broadband electric field structures. And so there have been a few different studies looking at things like kinetic Alfvén waves, field line resonances, time domain structures, showing here's the global distribution of those. So they have very similar distribution to the precipitation bands that are observed. And so this kind of pre-midnight peak from some of these processes as well that can scatter electrons ranging from keV to MeV energies. And so again, the question here then is, what's the relative contribution of all these various scattering mechanisms to causing these relativistic electron precipitation events that we observe at low altitude? And I did just want to highlight, so this relativistic electron precipitation distribution is observed by SAMPEX, as well as by a number of different balloon campaigns and by the POSE satellites. And when you compare this global distribution now to the distribution of EMIC waves that we see in the magnetosphere, you actually see that they aren't exactly the same, and that EMIC waves often occur primarily across the day side. And so this question of how many of these precipitation events are actually caused by EMIC waves, or how many of the EMIC wave events are causing precipitation events, is still pretty open in our field. So with that, I talked, I guess, a little bit about the background, and then also just about where we see these different types of precipitation occurring in the magnetosphere. So I wanted to move on to look at when and how much precipitation is occurring now. And so this question of when precipitation occurs relates directly to one of the motivations in the beginning that I talked about of how much is precipitation contributing to both the main phase very rapid dropouts in flux that we observe during geomagnetic storms, as well as to the recovery phase evolution of the outer radiation belts. And so here's a study by Horn et al. Looking at using POSE data to look at greater than 1 MeV trapped as well as precipitating particles in the pre-storm, main, and recovery phases of geomagnetic storms. And they find that the precipitating fluxes over here on the right, you actually don't get significant enhancement during the main phase when that dropout occurs compared to pre-storm levels. And it's really in the recovery phase that you see enhanced precipitating fluxes. There's also a superposed epoch study by Meredith et al. That looked at high-speed stream-driven storms in this case. And again, they're using the POSE measurements in the 90-degree and 0-degree telescopes. This top panel is looking at relativistic or kind of greater than 1 MeV electrons. And then they also look at lower energies, so greater than 100 keV, shown here on the second two panels. And what you can see on the right is that, so if we look at the 100 keV and above energies, you get an enhancement right at that 0 epoch time in the 0 to 90-degree telescope ratio. And so relatively more precipitation. But when they look at the MEV electrons, they don't see this necessarily enhancement in precipitating particles relative to the trapped population. And so this would suggest that maybe MEV electron precipitation is not contributing significantly to those main phase dropouts. But I did want to kind of remind you of that caveat that the 0-degree POSE telescope is not measuring the full loss cone. And so if you are getting diffusion of these particles just into the edge of the loss cone, you might not see it in this 0-degree telescope. So I wanted to highlight another recent study, this one using Van Allen probes measurements to look kind of statistically at these dropout events. And what they found using the phase space density profiles measured by Van Allen probes near the equatorial plane. So rather than looking at precipitation directly, they're looking at changes in the trapped population. And they found that during the dropouts, while there's evidence of significant loss to the magnetopause, they also see evidence for scattering into Earth's atmosphere, particularly at higher energies and smaller pitch angle particle populations. And lastly, just another kind of study looking at instead of kind of general precipitation measured at low altitude by POSE, this one using SAMPEX data and looking specifically at those microbursts or precipitation bands during, again, during high-speed stream storms and in a superposed epoch study to see how the occurrence as well as magnitude of these two specific precipitation types changes over the course of the storm. And here we found that microburst occurrences increase significantly, particularly in the recovery phase of storms, while their magnitudes are relatively constant throughout this pre-main and recovery phases. And so this is consistent with chorus waves, both as a generator of microbursts as well as a source of local acceleration during the recovery phases of storms. The precipitation bands, on the other hand, occurrence rates were increased slightly during the main and recovery phases of the storms, but it was really the magnitude of these precipitation bands that increases during that main phase, particularly at the inner edge of the outer radiation belt, which suggests that precipitation at these kind of lower L shells may be contributing to those main phase dropouts. And so overall, there's kind of a lot of different ideas about how precipitation of different types and different energies may be contributing throughout geomagnetic storm phases. And we really need to better reconcile these various different observations, both of trapped phase space density populations as well as low altitude measurements, to understand whether precipitation is contributing to radiation belt dropouts, and if so, what type of precipitation and at what energies. So moving on, I also wanted to touch a bit on how much precipitation is occurring. So one of the key steps for both radiation belt and atmospheric chemistry studies is to better quantify the loss to the atmosphere. And there's been a lot of progress on this, particularly recently, as we're able to combine multi-point measurements from a number of different low altitude observatories, including CubeSats, as well as balloons and ground-based observations. And one of the key steps towards quantifying precipitation loss is to be able to better constrain the spatial extents of precipitation regions. So to understand over what kind of range in L shell and local time and time, or UT, is precipitation occurring, and then you can use that to help quantify. And so I wanted to highlight a few different studies now that have constrained both the precipitation bands as well as microburst spatial scales. And so on the left here, there have been a number of studies combining measurements from the Colorado Student Space Weather Experiment CubeSat, from the Firebird CubeSats, from the AC-6 CubeSats, as well as the Barrel balloons, and the POSE spacecraft to map out the spatial extents of these precipitation band type events. And what is found is that they're often very narrow in L shell or radial extent, but can be extended in local time or UT. And this middle panel shows a study of POSE data following up on some studies by Shekhar et al. So this one's more recent, looking at the 2-second POSE data that shows that the extent of these MEV electron precipitation events is often quite narrow, so less than about 0.3 in L shell. And then lastly, this study by Anderson et al. Looking at the actual spatial extent of microburst precipitation. So here he's looking not at the individual microbursts, but over what kind of local time and L shell ranges are microbursts occurring in general during an event where They had measurements from the Firebird CubeSats, the AC6 CubeSats, as well as one of the barrel balloons. And what they found is that while individual bursts are often short-lived, these larger scale kind of microburst regions can be quite extensive and last hours. And so these precipitation spatial extents can be then compared to wave spatial extents to better understand how the scattering mechanisms might relate or cause these spatial extents. And so there have been studies comparing that kind of radially narrow but locally extended in local time precipitation band type event to EMIC wave spatial extents, which also are often observed to be radially localized but persistent in local time or UT. For microbursts also, I wanted to highlight that there have been studies not just on that general spatial extent, but on the individual spatial extents of individual microbursts, so those kind of sub-second events, comparing measurements from low altitude to individual chorus rising tone element extents. And what they found is that microburst extents are often on the order of about 10 kilometers at low altitude. And when you map this to the equatorial plane, it's in good agreement with that spatial extent of chorus rising tone elements. And so finally, we talked about kind of when, where, and how much, but I did just want to highlight some of these other open questions. One is what fraction of precipitation is driven by specific waves or wave modes. And I touched on this a little bit when we talked about field line curvature scattering mechanism, as well as those more broadband electrostatic features. And so there have been a number of studies trying to disentangle or better quantify how much of precipitation is driven by what different types of mechanisms. I also wanted to just briefly touch on the question of the energy spectrum of EMIC and chorus wave scattered electrons. And so if we look at EMIC wave driven precipitation, kind of a classic cyclotron resonant interaction between EMIC waves and electrons suggests that you should only get this resonance above energies of around 1 to 2 MeV, so that EMIC waves should primarily be a scattering mechanism for these kind of multi-MeV electron energies. And there's certainly some observational evidence suggesting that this is the case, but there have also been recent observations suggesting that lower energy electrons, so in the kind of tens to hundreds of keV energies, may be associated with EMIC waves, and that there are potentially non-resonant or non-linear interactions that could drive this kind of lower energy precipitation from EMIC waves. And so this question of what energies are actually scattered by the waves and what is that interaction between the waves and the particles that can scatter these different energies is still kind of a topic of much debate. On the microburst side of things, there are also questions about the energy spectrum of particles that are scattered by chorus waves and what is actually measured in the microburst population. So the Firebird CubeSats and this STSat-1, this Korean satellite, both examined the energy spectrum of microbursts, but focused in the kind of hundreds of keV energy range. But early SAMPEX measurements raised questions about the relationship between the MeV electron and the kind of lower energy tens of keV electron microburst events, because there was not always a one-to-one correspondence between the two. And so there's a question of whether these MEV electron microbursts that are observed are really just the high energy tail of lower energy microbursts, or whether they're caused by different interaction. And on that note, I wanted to highlight some recent results by Mike Shumko et al. Looking at this connection between lower energy electron precipitation and higher energy MEV electron microbursts. And so he looked at SAMPEX passes over these all-sky imagers looking at auroral features, often pulsating or patchy aurora, and found this correspondence between when MEV electron microbursts were observed and enhancements in the all-sky imager intensity, suggesting that there is this connection between the kind of highest energy end, the MEV electron precipitation, and the lower energy few to tens of keV precipitation that would be causing the aurora that we observe. And so with that, I just wanted to take a very brief look at what's next and what, so I've mostly focused on some of these open questions and kind of outstanding questions in relating to energetic electron precipitation. But there are some upcoming efforts to try to address some of these questions. And so I wanted to just highlight 3 different efforts. One is the Living with a Star program has a focused science topic starting this year, looking in particular at understanding and predicting radiation belt loss in the coupled magnetosphere. And so there are a number of different groups involved in this topic, approaching the question both from a modeling and data analysis perspectives to try to better understand how much precipitation may be contributing to radiation belt depletions compared with magnetopause losses. The other is an effort led by Alexa Helford at Goddard, looking at space precipitation impacts. So the impacts of low, medium, and high energy particle precipitation on Earth's atmosphere. And so this will combine theory modeling and data analysis efforts as well as well as some upcoming observational studies to better understand how these particles are impacting Earth's atmosphere. And then finally, there's some upcoming missions that will take measurements that will really help us answer some of these precipitation questions. And so there's, this is probably not a comprehensive list, but the SNIPE CubeSat constellation from Korea should be launching in this next year. And they'll be better mapping the kind of energy spectrum and spatial extents of microburst precipitation. CERBI and REAL and APEX are all upcoming CubeSat missions as well that will study energetic particle precipitation and provide more information about the high energy resolution, pitch angle resolution, as well as spatial extents of these observations. And so with that, I did want to just end here and leave time for questions and discussion because I do have to go right at the top of the hour. So I'll stop here and open it up for discussion. Thank you.
Excellent. Thank you so much, Lauren. This was great timing. And as you mentioned, there are already a handful of questions that have come in here. And before we jump into the questions, I do want to mention, especially for our YouTube viewers or YouTube subscribers, we tried out a live chat feature as well there. So I'll keep an eye on that in case anybody on the YouTube side has some questions too. And I'll also mention that, of course, next week, feel free to tune in. We have Jean-Francois Ripoll is going to be talking about radiation belt modeling as well. All right, so with that, some questions. Kyle started us off here wondering, are the quasi-trapped drift lost cone particles lost in the red region of the plot, or can they be lost anywhere along their drift orbit? And I think this was an earlier plot where you showed kind of a map region and there were red, green, and blue populations on that
slide. So
So
let me see if I can pull up that slide in particular, but the answer is that they are lost in that red region. And so these different particle populations are really, they exist because of the kind of offset nature of Earth's internal magnetic field. And so there's actually a decrease in the magnetic field strength around this South Atlantic anomaly area. And so a particle that is kind of quasi-trapped or just on the edge of the lost cone, as it drifts around, it will reach a lower magnetic field strength when it passes in this area. And so it will precipitate here. The red region, actually, those particles are in the bounce loss cone. And so if they're measured as locally mirroring in the northern hemisphere. When they reach the southern hemisphere, they'll precipitate. And so it's actually this kind of green blob that where precipitation occurs from the quasi-trapped population.
Okay, great, thank you. And so next, Patricia was wondering if the pitch angle distribution is nearly isotropic and large, though, doesn't that mean that the diffusion into the loss cone is maximal? And I think that was for the storm phase titled slides, a few slides after that one. And if you need more clarification, we can have Pat unmute too.
Sure. So,
so you were saying that it was not important because it was nearly isotropic, but I would say, since the flux was really large and it was isotropic, it is important when you're talking about the phases and the recovery phase fluxes.
Yeah, absolutely. So I wanted to pull up this slide to show that, yes, you're right, that when the flux is isotropic, so when you have nearly equal fluxes in that 90-degree and 0-degree telescopes, that is when you're getting kind of maximal precipitation. And so that is when you expect the most precipitation flux. So in the storm phases, I'm not sure I talked about isotropy much here. I think we were looking more at when
the next one, the next one.
Yeah, got it.
Slide.
Yeah.
You said you didn't think that was important, but it looks like that's where it's maximum fluxes. So maybe I just misunderstood you, but I thought you said it wasn't important in the recovery phase, but it sure looks like big fluxes to me.
Yeah, so at these lower energy, high energy electrons, so hundreds of keV, you are getting significant precipitation or a high ratio of 0 to 90-degree fluxes during the recovery phase. But at these MeV or greater than 1 MeV energies on the top two panels, you actually don't see that enhancement in the 0-degree telescope. And so that's what I was trying to highlight in this study, that they don't see significant multi-MeV fluxes in the main or recovery phase of these storms. Okay,
great. Thanks for jumping back to those slides. And then actually the next set of questions here, I think 3 of them are all Aurora related. So starting off with Jason here, and Jason was wondering, is it known what proportion of the electron precipitation is caused by kinetic Alfvén wave scattering of the electrons into the loss cones?
Absolutely not. And that's one of the kind of big questions. I think it's a more recent, there have been more recent studies looking at these kinetic Alfvén waves, and Chaston et al. Has a few papers, this 2015 one, but some subsequent ones as well, showing that they can scatter electrons into the loss cone. But quantifying this or figuring out when and how much loss is caused by this process is really an open question for now.
Great, thank you. And here are the Aurora ones. So Jason also wondered, what role do the microbursts play in auroral substorms, if any? And I think you may have mentioned some of this on the Shumko et al. Slide.
Yeah. So I think that's also another kind of big open question right now. In general, I'd say chorus waves are often associated with substorms and substorm activity. And so there's that relationship. And then chorus waves are also associated with microburst precipitation. But that link between kind of auroral forms and microbursts is still less well studied. You know, there's the aurora and chorus, or substorms and chorus, and then chorus and microbursts. But I think this Shumko paper, and then there's another recent one by Miyoshi et al. And some of our Japanese colleagues involved in the Arase mission that are starting to look more at the relationship between, in particular, pulsating aurora and microburst precipitation.
Actually, it's a perfect segue into Eric's question about the pulsating aurora. Eric was also wondering, has anybody proposed a causal mechanism for why microbursts might be correlated with this pulsating aurora?
Yeah, so I think the causal mechanism would really be the chorus waves, or, the drivers of the precipitation, both at auroral energies and at these high energy microbursts. And so chorus waves can resonate with and scatter the kind of tens of keV electrons that would be involved in pulsating aurora. And then they can also resonate with higher energy electrons and scatter them into the loss cone, generating microburst precipitation. And so that is one kind of hypothesis that Shumko et al. mention in his recent paper for this connection between pulsating aurora and microbursts.
Excellent. Great. Well, let's see, we have one more rolling in here just before the top of the hour. So Jason was also wondering, have the timings of the various auroral stages been looked at in comparison with the microburst precipitation events?
That's a great question. And I'm kind of less familiar with the auroral studies and more familiar with kind of radiation belt and geomagnetic storm studies. And so to my knowledge, I don't think I've seen studies looking at microburst precipitation as it relates to auroral stages. It's been more focused on as it relates to the phases of geomagnetic storms like I showed. But if someone else on the line has more information or wants to join in on that topic, please feel free.
Great. Okay, well, we still have a couple minutes for the top of the hour, but I think just to be respectful of your time, we'll leave it there. And of course, if there's follow-up questions, they can reach out to us at our email. And just want to, again, thank you so much, Lauren, for a terrific presentation and overview of some really exciting research that's been happening. And so, yeah, with that, thanks, everyone, and hope you have a great week.
Great, thanks so much.
Yeah.
Thanks, Lauren. Have a wonderful week.
Thank you, you too.
Thank you.